Okay, number 5 asks an electrolytic cell contains inert electrodes, so those aren't going to react in a solution of acidified copper nitrate. So either of these can react, and I believe water is also potentially something it's going to react with. There we go. So when doing this, you have to look at all things that are available. You ignore the electrodes. So we're talking about Cu2 plus, 2 NO3s. But actually the 2 doesn't matter so much, it's NO3. And you have to look at water on both sides because water can do either. And when you look at this, it's quite annoying to figure it out because you could easily say, well, there's an NO3 here and there's an NO3 here. Which one do I use? And generally speaking, you have to, I believe you have to pick the one that is furthest away. Yeah. So then you can see this is here. And then if you look closely, water technically is here. You have to consider it's really up here at about 1.375. And then the copper 2 plus, you can see, is over here. That means copper is going to react. Oh, you also have to consider the other water further down here, which means the copper is going to react with the water, or it's potentially water and water is going to be electrolyzed. But then you have to look at the things that are bottom left, closest right. So when you consider this is actually up here and that they're only 0.41 away, then the only ones that could react is the NO3 here and the water. So this NO3 is closer. So that means you're using this one, 0.96, 1.375. And the water's got to go that way. So if you rewrite it, and for some reason your book doesn't balance the electrons. Personally, I think it's a good habit, but I think they just don't want the students to get confused. So that's one reaction where we're using, and its voltage is 0.96. The other one we're using is this one, backwards. There we go. And its reverse is negative 1.375. When you add those up, we're talking about a negative 0.415, something like that. That means you need at least 0.415 volts to get this reaction going. If you technically were to balance it, you have to multiply everything here by 3 to get that, and here by 2 to get that. And then if you were to add the 2 half reactions, because you get questions like that, I'll skip the minuses. We don't need the electrons, that's why we did it. Then you notice that there's 8H plus on the left and 6H plus on the, sorry, 8H plus on the left, 6 on the right. Get rid of 6 of them, and that would be your balanced equation with 6 electrons being transferred. Because that will come up in the other equations like the Faraday equations, the Ernst equation. You'll need to know the number of electrons. 10 is also annoying a little bit. You sort of have to get used to what you're being told. I'm a little bit surprised he's used this 2 examples because there are better examples of of electrolysis, but a type 3 means neither electrode is inert. They've told you right in the question that we're putting aluminum, we're putting silver on an aluminum. which means my silver has to come from here. I can make any solution with silver, and I can choose another substance here that won't react. So I don't really even have to worry about it because I can control what solution I'm using. And this should also be silver because as electrons get ripped off of it over here, and as silver gloms on here, more silver ions will dump into the solution. So I'm essentially transferring this electrode over to that electrode. Since the electrons are going this way, and I know they're going this way because Ag plus has to plate onto this. To do so, it has to go from an ion to a solid, which means that up here I would draw my, since I know the electrons are going that way, I know that this must be the cathode of the battery, this must be the anode, and this must be the cathode in the system, the cathode electrode. This must be the anode electrode. And I know that silver is glomming on here. You might say, why do I know this is silver? Because it makes the most sense that if I want to continue plating this, I need a source that's going to dump into the solution into ion form. So I would then look up Ag plus, because Ag is both the reducing agent and the oxo being reduced and oxidized. You would discover silver right here. And again, this just gets instinctive about what they're looking for. And to write it, you would write them in both directions. It makes the most sense this way because you have two inert, that means the second reaction's at negative 0.8. You have two reactions, and the whole goal is to plate the aluminum fork with silver, so you might as well have an electrode that's providing more silver. You notice that this adds up to 0, but technically all of these systems require slightly more than whatever's being added up. Kind of breaks the rule about the negative thing, but kind of shows why we need more electricity, more energy than is shown by adding these. Oh, what's the voltage? 0. That's the predicted voltage, but again, you always need more. On inspection of your SRP table, you discover that you would circle all your waters, water here, Cu2 plus. Technically, you circle that one too, because this is just one electron, this is 2 electrons. And then you have your Br minus here, and your water is technically up here. Now, if you look closely, the most left, closest to the top right, are these two, as opposed to this one. So you know it's this reaction going to happen. So you write the bottom one as normal, because it's the reverse of what a normal chemical reaction is happening. So that means the Cu2 plus is being reduced. Into Cu2 solid. And it has the normal voltage. And it also means that the Br minus is being oxidized. And it's reversed in terms of its charge. When you add those two charges together, you get negative 0.75, which means you need at least 0.75 volts or more to make this happen. The other thing that's interesting is they didn't ask us to draw it, but they should have. And these are inert electrodes, like this. The solution is here in with water. We know that the thing grabbing electrons is the copper. So let's just put the cathode on the right. So I might have put it, oh yeah, don't forget to put your thing here. So let's just put it on the right. I was putting it on the left before, it doesn't really matter. And the anode. Cathode is always the source of reduction, and the electrons are always going from the cathode, sorry, from the anode to the cathode, which means up here, the short stick, I believe, is the anode, and the long stick is the cathode. So you draw your battery like that. If they ask for the directions of flow, you put some sort of arrow like this with 2 electrons flying around. Let's say 2e. The C, sorry, yeah, the Cu2 plus would be getting electrons here and coating this cathode with copper. And then over here, it would be coming from solution. And what's interesting here is this Br minus would be grabbing, or yeah, losing electrons here and becoming a solid. I don't know if it's solid on there or solid on the anode. I think it would be naturally have to go to the anode to donate its electrons. I don't think they ask us to draw it. Let's go check. 12, was it? Yeah, they just want the half reaction, the voltages. It certainly doesn't hurt to sort of draw that, though, and to show where things are happening. That's the questions for 7.5.